In this video, we'll be looking at vapor pressure, temperature, and enthalpy of vaporization, which are all related by a substance's intermolecular forces, and they're all actually put together in one useful equation called the Clapeyron equation. We'll actually be doing a lab where we get the heat of vaporization of water by collecting vapor pressure data and temperature data. So if you have temperature and pressure, or yeah, temperature and pressure data, then we'll be using this form of the equation. And it looks like this. It's you actually take the natural log of the vapor pressures, and you take an inverse of the temperatures, um, and you'll see that the way this is written is actually in a familiar form of the line equation. So it's y is actually, so on the y-axis will be the natural log of vapor pressures, which is equal to the slope. So the slope is actually equal to the negative enthalpy of vaporization divided by r times x, which is the inverse temperature, and plus c, which is like our shift number. One note about R that we'll be using. So the R that we use in this equation is 8.314. So it's the energy form of R. And we know that because the enthalpy here is always measured in energy per amount. So energy per mole, joules per mole. So that's why we need to be using this R value. Um, let's see. Another thing to note is that now that we see that R has K as Kelvin in here, I'll use a different color pen to show that the temperature here, it needs to be in Kelvin. So this must be in Kelvin. And typically this is like a problem where you're plotting data, and you plot this on the y-axis, you plot this right here on the y, and then you plot 1 over temperature on the x. And you can use your TI-84 and figure out what the line of the equation is, which we're interested in because we want to know what slope is so that you could solve for delta dHvap. So in other words, you use this equation a lot to solve for delta dHvap, where and what happens then is m would equal, you set the slope equal to this, the enthalpy of vaporization over R, and then you could easily solve for enthalpy of vaporization. There's another form of this equation, and this is if you know 2 points of data and you want to know what the final point is. So here's the equation, and then I'll try to describe like an example problem where this would be useful. So it's the natural log, and it's really the same equation. It's just a little bit converted. The vapor pressure at one temperature over the vapor pressure at another temperature equals um, the enthalpy of vaporization over R times 1 over the second temperature over, minus 1 over the first temperature. And when would you be using this equation is when you have a problem such as this. Let's say you know that at 25 degrees Celsius, let's say at 25 degrees Celsius, we know that water's vapor pressure is like 30 torr, for instance. Okay, and you could use this equation if you want to know. Let's say you want to know what you're interested in. What is the vapor pressure of water at 60 degrees? What's the new vapor pressure? Okay, so if you wanted to know that, so we have actually 4 variables, 1, 2, 3, and 4, and we know 3 of them, 1, 2, and 3, and then you could solve for the fourth using this equation. So, and of course you would need to know what the enthalpy of vaporization was as well. So your T1, it actually doesn't matter where you plug T1 and T2 at actually, just as long as you keep the vapor pressures consistent as well. So, so T1, for example, would be 25. So again, this has to be in Kelvin, so that would be 298 Kelvin if you were to try to solve this problem. T2 would be 60, which is 333 Kelvin. And then pVap has to match. So where we plugged in 25, that has to match this number right here. So we would plug in 30 torr right here. Okay, and then we would know this value. Okay, and then we would our unknown then in this case would be this number, and then we could solve for that using some algebra. So so that's what you would use this for. So I'll make a note of this. So you would use this if you're interested in usually a vapor pressure at some second temperature, given that you know the vapor pressure of it at a different temperature. Okay, so the next slide we'll be going over into a little bit of theory about where this equation comes from, and what some of the numbers, what some of the values actually mean. So on this graph here, we see unconverted data. By unconverted, I mean just the vapor pressure is plotted versus temperature here. And then here on this graph, we see the same substances, and the data for them has been converted to natural log and 1 over the temperature in Kelvin. So I wanted to point out a few things here. On this graph, we see that let's just pick a temperature like 30 degrees Celsius. Okay, and if we go up here, we see that water at 30 degrees, the vapor pressure is less than 50. So 50 is about right here. So the vapor pressure of water is around 25 torr. Okay, and then let's keep it at 30 degrees, and we see at ethanol, it's around 100 torr. And if we keep going up and look at this other substance, diethyl ether, we see that it's around 640 torr, a massive 640 torr. So at the same temperature that water would be 25 torr. So from our previous tutorial, we noticed we made the point that as IMFs get better, the vapor pressure will decrease. So when something has really bad IMFs, like diethyl ether, it's going to have more vapor pressure at a given temperature. So let's take a look at diethyl ether. It looks like this. So it's a diethyl. So it's a CH3, and then a CH2, and then it has an ether functional group here, surrounded by these nonpolar pieces. So diethyl, which means 2 carbons long, and it means 2 of them. So it's got diethyl, and then this is an ether functional group. So we see that it can do dipole-dipole. So this will do dipole-dipole. However, these big bulky nonpolar side chains get in the way of any effective dipole-dipoles this can do. So this is going to have really bad IMFs. This is a diethyl ether. Okay, so this has bad IMFs, and we see the result on this graph. When you graph the vapor pressure, you see that at 30, something with good IMFs like water is sitting at 25 torr, whereas diethyl ether is 640. And ethanol, you'll see, if I draw out ethanol, it's 2 carbons long. Okay, and it'll have an OH. Okay, so it'll have 3 H's here, 2 on the middle one. Okay, and this guy can do hydrogen bonding. So hydrogen bonding, but this part right here is again is this nonpolar bulky chain that gets in the way of really good hydrogen bonding that this can do. So although it can do hydrogen bonding, it's got this nonpolar portion that kind of makes it have bad IMFs as well. But as we see on this graph here, it's not nearly as bad as diethyl ether. And then of course we have water, which has the highest boiling point. So it's showing at 760. This dotted line right here are the boiling points. So of course then we have water, which can do the special thing about water is although it's small, it's really, really good at doing every little bit of it is polar, so it can do really nice hydrogen bonds. And we see that at 25 torr, at 30 degrees, the vapor pressure is only 25 torr. So let's take a look at the converted one, and this is graphed using, this is what a graph would look like by using that Clapeyron equation, negative delta HVAP over R times 1 over T plus C. So you see that you have a negative, you're going to end up having a negative slope here, so it's going to go down. Um, and let's take a look and see what, and remembering while we're looking at this, that this is slope. So diethyl ether, remember, this has the worst IMF, so what do we see? Um, we see the most gradual slope. So we see this is the least steep slope here. So diethyl ether has the the least steep slope, and then water on the other hand has the most steep. So water is this line, so this is the steepest that we see. So it has the greatest like rise over run out of any of these. So what that means is its m value, the slope value, is going to be big. So when we go to solve for delta dHvap, the enthalpy of vaporization, you'll see a bigger number. So we can make a conclusion that we made, which matches the same conclusion we made on our previous tutorial, and that's when IMFs are good. So when you have good IMFs, this results in a steeper slope on this graph. And then when you go to solve for the enthalpy of vaporization, you get a higher value for enthalpy of vaporization, meaning it takes, and remember the units for enthalpy of vaporization is typically kilojoules over um, kilojoules over Kelvin times mole. Actually, no, Kelvin's not in there because there is no change in temperature. So it would just be kilojoules over mole. So that means it takes more energy to break IMFs and get it to boil the whole substance to change phase. Okay, and this makes sense when we look at the slope that we see a steeper slope, and then when we look at diethyl ether, this makes sense with this curve right here. When you convert the data, you'll see the slope with the least steepness to it, which matches its really bad IMFs. Okay, and then that should give rise to a lower enthalpy of vaporization when the IMFs are not as good. Okay, so let's try an example problem. And here we have some plotted data. And so we're going to end up using, we're going to plot these points and these points in our TI calculator and see what we can get for the enthalpy of vaporization. So if I go back to a couple slides, and that problem is actually this type of problem here. Okay, so we're going to plot the temperatures in the x-axis, and then we're going to plot the natural log of the vapor pressures in the y-axis. So let's get to this problem. Um, and I'm going to open up our calculator here, and Let's turn this on. And let's go to so to start plotting points here, we go into stat and we go to edit. Okay, and let's clear anything else that we had in there before. And what I'm going to do here is add, I'm going to put the um, L1, I'm going to put our temperature data since our calculator defaults with L1 being the x-axis. And remember to, of course, convert this. So we're going to type in 1 divided by 273, and remember to change it to Kelvin. 273 plus 750. Hit equals. Okay, I'm going to do this for each one of the temperatures. So 890 plus 273. And our next value that we get is 1080 plus 273. And let's see, 1080, now 1240. So 1 divided by 40 plus 273. And then our next value, one more, plus 1310. Okay, and now we're going to go to our vapor pressures, and we're going to convert that to natural log. So natural log of 1, and just do this for each one of these. 10, natural log of 100, natural log of 400, and natural log of 760. Okay, and now we have our data, so we're ready to plot. But first we need to turn on our plot. You don't actually really need to graph it at this point, but I do want to show you what it ends up looking like. So I go second function stat plot, and I see that I already had this on from when I was doing this before. So if it's off, we just hit enter. Okay, by default this is going to be off, so you switch it over to on. Okay, and then also by default it's on the scatter plot. So we want the points to connect to see if we get a linear result. Our X list is defined as L1, and then Y list. So if you actually put these in to the X to the L1 list, you can actually change it right here. Okay, so but I actually put this one in our L1, so we're good to go here. So now I go over to graph. Okay, and we see our points here. What you guys are probably going to see is you guys are probably going to see the graph look like this because the standard scales are a lot bigger than normal. So how do I get this to zoom in? I go to zoom here, and then I go down to Z stat, or I'm sorry, it's called zoom stat. And what this does is the calculator knows it will like auto adjust in order to fit the graph in to what we need. So I'm going to hit enter. Okay, and then now we have our nice linear relationship. So if you noticed, our data points were very very small, so that's why our graph was really zoomed out. So what I'm interested in though is our line equation. So I go over to stat, and then I go over here to calc. So I'm going to scroll to calc, and then I'm going to scroll down to number 4, or actually I could just hit number 4 here. And our X list is L1. So again, you have to make sure that the L1 and L2 are correct. So if you're getting these wrong and you don't know why, just make sure double check your lists are defined correctly. So ours are defined correctly. So I'm going to go down to calculate and hit enter. And there's our slope. So this is our slope. I'm going to write this down and set it equal to negative enthalpy of vaporization over R. Okay, so over here on uh, my work here. So I'm going to go m equals negative 19,038, which is equal to negative enthalpy of vaporization over R. Okay, and then solving for enthalpy of vaporization, I get 19,038 times R, which is 8.314 joules per, actually, yeah, per Kelvin times mole. Okay, and I believe these wind up, the unit for slope ends up being Kelvin. I'm not quite sure, to be honest, but I do know my units for enthalpy of vaporization should be joules per mole here. So let's go ahead and type this in. So 19,038 times 8.314. Okay, and I'm going to convert this to kilojoules, so I get 158 kilojoules. So this equals 158 kilojoules per mole for lithium. All right, so I'm going to have you guys go ahead and do the same that I just did on your TI calculator. If you have an Android phone, you could download an app called Wabbit Emu, and it's free. Just look for it in the Play Store, and it'll put a TI calculator on your Android phone. And if you have a PC, you could get the same application. You could just do a Google search for Wabbit Emu, and they have the same application running on Windows. I'm not too sure about Macs or Apple Apple iPhones. So anyway, try this. You could even do this on Excel, actually. So try this in your calculator, or you could go really old school and pull out some graphing paper and start graphing this. You could do like a rise over run here, and then calculate what the slope is going to be. So you could do it that way if you don't have a TI. So do it for this, and what the question is which metal is the bonding stronger? So remember, if you improve IMFs, they're harder to um, you increase the intermolecular strength of the bond, so it's harder to boil it, which gives rise to higher enthalpy of vaporizations. So you need to figure out what the enthalpy of vaporization is for magnesium, and then you can compare it to this number. Okay, so good luck on the finishing off this problem. I'll like to see what you guys come up with. And that's the end of our tutorial.